day, everyone. My name is John, and today I would like to talk to you about gray matter age prediction as a biomarker for risk of dementia. As most of you will know, the brain continuously changes with age. As an example, the hippocampus is shown over here, where aging reflects into shrinkage of the structure. This means that the brain holds information on and can be used to estimate the age of a person. However, neurodegenerative diseases and dementia also affect brain structures. How would this affect the information retrieved from the brain on a person's age? Recent studies have shown that a gap between predicted brain age and a person's actual chronological age is able to distinguish case from control groups, indicating that this gap may serve as a biomarker for neurodegenerative diseases and dementia. As a next step, we want to take a longitudinal approach in brain aging over time. Thus, we aimed to investigate the utility of such a gap as a risk biomarker for instant dementia. For our study, we used an artificial intelligence technique called deep learning to build a model that takes in 3D brain images to predict its age. The data we use comes from Rotterdam study, which gives us access to MRI scans of more than 5,000 participants. All this data was used to train, validate, and test our model. Additionally, we have a set of 159 participants who developed dementia later on. Having built the model, we can show its performance in the graph over here. Here we see the predicted age based on brain image against the respective subject's chronological age on the x-axis. The red dots represent all the subjects in the dataset, and the dashed line represents a perfect prediction. Prediction performance was similar to studies mentioned in the introduction, with a mean error of around 4.5 years and a high reproducibility score. Now, using this model and the data we have on the participants with incident dementia, we can assess the association of the gap with incident dementia using a Cox proportional hazards model. This model gave us a hazard ratio greater than 1, indicating that an increase in gap is associated with a higher chance for incidence of dementia. Additionally, we can show the Kaplan-Meier curve. The quintiles of the gap values illustrate the difference in dementia probability between the lower and higher gap values, where lower quintiles or low gap values had a higher probability of being free of dementia. Lastly, we note that the interpretation of the gap is still a bit challenging. What is it exactly based on? But because we have used a deep learning model, we can apply visualization techniques to trace our results back to the original image and retrieve the attention maps. These show that the amygdala and hippocampus were particularly important for brain age prediction, thus giving us a visual feedback on the deduction. Concluding, the gap is a significant biomarker associated with a risk for dementia. Higher gap values were associated with a higher probability for developing dementia later on. Secondly, deep learning approach allowed visualization of brain regions which were important for aging. This can be useful for future research to investigate the relation between brain regions and dementia. As such, we believe that this research and its approach can help us understand the human brain a little better. Thank you for listening.